Hi, I'm Shaul. How can you tell a poppy lens from a flat one without even trying them? Well, first of all, let's have a look at some lenses and compare. Those are two 20-ish millimeters lenses. The poppy one is on the left, the flat one is on the right. "28 millimeters, poppy on the left, flat on the right. 35 millimeters, poppy on the left, flat on the right. And 40 millimeters. The one on the left is poppy, the one on the right is flat. The larger lenses, like this one, are designed for digital reflex cameras. So they are autofocusing, but still they are much larger than these ones. These lenses are designed for rangefinders, so they are manual focus, and because of some characteristics of rangefinders, all lenses have to be small to minimize the viewfinder blockage. But still, differences are quite considerable. So why do those lenses have to be so large? Well, there are two things here. One is they are wider, thicker, and that is due to a limitation of digital sensors. In order for the image to be harmonious, which means that the corners are as bright and as sharp as the center of the image, the light hitting the sensor has to be perpendicular. So the light rays are hitting the sensor in a close to a 90 degrees angle. And the designers of those lenses address this problem, this challenge with brute force, which means the lenses project a larger circle than the diagonal of the sensor. So what you see in the image is only the central part of this projected image, and the light coming from the periphery of the lens is thrown away. So the focal length of these lenses is actually wider than the stated focal length, and this 20 millimeter lens is a good example. It has quite a bulbous front element which suggests that it is wider than 20 millimeters, probably about 16 millimeters. The image is slightly cropped, so only the central part of the projected image circle is captured by the sensor. This is quite a positive thing, because for landscape photography, architectural photography, you actually look for an harmonious image. It is important in these genres to minimize the vignetting or field curvature. So these lenses are addressing that quite successfully. Lenses built for rangefinder and mirrorless systems typically use a more elegant, economical approach to the problem of angular light coming from the periphery. They utilize a large diameter aspherical element at the rear of the lens to pick up peripheral angular light and straighten it. But then why are those lenses so much longer than these ones? And to understand that, we have to go back to characteristics of the glass itself. If we look at the design of those DSLR lenses, we will see that they contain a lot of extra low dispersion glass. Anything between 25 to 50, 60% of the glass used is low dispersion, extra low dispersion. Now, there is a linkage between dispersion and refraction. Both of them have to do with the glass changing the angle of the light hitting it. But refraction relates to the total light, and dispersion reflects to the differential effect on the angle depending on the wavelength. So it's a micro phenomenon that causes a rainbow effect. Generally, to reduce this dispersion effect, you want a special type of glass that is low density, which has a minimal effect on the angle of the light and of the separation of light. So the problem is that when reducing dispersion, you also reduce refraction. And since the main function of the glass element is to change the angle of light, to focus it or to disperse it, This extra low dispersion glass is not as efficient in changing this angle as heavier, denser glass. So the curvature of the elements has to be stronger when you use this type of glass, which creates other problems like spherical aberration, which means that light coming through the center of the element or the lens does not focus in the same distance as light coming from its periphery. So typically in lenses with high content of extra low dispersion glass, you also need to correct spherical aberrations by using more elements, specifically more aspherical elements, which are designed to compensate for this effect. So in general, those lenses are made of many more elements that correct each other to produce a well-corrected, acceptable image. Those lenses, on the other hand, use a high proportion of high-density glass, which doesn't need to be as curved to achieve the same effect. So you can make them a lot shorter. Extra low dispersion glass actually diminishes the dimensionality of images. Of course, dimensionality is only an illusion. It's not really there. All photographic images are flat, are two-dimensional. But still, in some images, we perceive the three-dimensional nature of the scene. And to achieve that, we need a natural transition, tonal transition from shadows to highlights. By natural, I mean gradation that is similar to the gradation that we see with our eyes. And second, we need slight, very thin transitions or blurring on the edges of surfaces. And both of these are achieved by denser glass, by high refractive index glass. With such glass, we get some chromatic aberration, though. There's no good way to avoid it completely. Of course, there are optical designs that minimize chromatic aberration, even without the use of extra low dispersion glass. For example, the achromatic doublet, which is a group made of two elements with different refraction or dispersion qualities that are cemented together and can affect or reduce the dispersion without a dramatic effect on the refractive index. But those solutions are less efficient in minimizing dispersion compared to actual low density, extra low dispersion glass types. Too much extra low dispersion glass in a lens will cause an abrupt transition from shadows to highlights, which does not look natural to the eye. It's very different from the natural tonal gradation we are used to see in real life with our own eyes. So the representation of curvature of surfaces looks unnatural, and correct perception of curvature is very important for the perception of three-dimensionality. This is how we estimate the shape or the form of objects in our daily life with our eyes. The second thing is the eye is not very sensitive to dispersion or to chromatic aberration. So when we see two surfaces, one closer to us than another, there is a thin transition zone that appears between those surfaces. It is also an important cue for the perception of 3D. It's something we developed in millions of years of evolution. When an image appears without this thin transition zone, it looks flat. So this is the effect of too much low dispersion glass. According to my own tests, and I did compare the 3D-pop effect of 50 different lenses, the percentage of extra low dispersion glass out of the total glass used in a lens explains about 70% of the variability in 3D-pop, which is quite considerable. The other 30% remain unexplained, but I suspect it relates to the percentage of high refractive index glass used in the lens. The problem is manufacturers don't really advertise the types of glass they use in a lens, except when they do, but we'll get to it later. So you have to rely on other things like the complexity of groups. Most complex groups using lenses, which are groups that contain more than one element, are designed to reduce chromatic aberration. And they do contain two pieces of glass with differing refractive indices. So the number of complex groups in a lens is a good indication of the existence of high refractive index glass. So you should really look at the average complexity of groups, which is the division of the number of elements into the number of groups. And the higher this complexity, the more 3D pop you will get, provided the percentage of extra low dispersion glass is kept to a low level. 10% of the entire glass or less. To get a good estimate of the poppiness of a lens, there is no way around looking at the lens diagram, I'm afraid. What I suggest doing is looking at the diagram and using the following decision tree. First of all, count the number of low dispersion glass elements in the lens. If there are more than 3, the lens is flat. It will be extremely flat. You will not be able to do anything to fill it with juice or life. If it's less than 4 low dispersion elements, you have to estimate the percentage of extra low dispersion glass used in the lens. It's quite simple. Just look at the cross section of the lens and try to evaluate how much such glass is used. You have to look at the number of elements and their relative thickness. So, if the lens contains more than 10% extra low dispersion glass, it will be probably mostly flat. If it's less than 10%, you have to next calculate the average group complexity. This is done by dividing the count of elements into the count of groups. So, if the result is less than 1.27, the lens will be mostly poppy. If the result is more than 1.27, the lens will be highly poppy. This is what I'm after. So I use this decision tree a lot, and so far it hasn't really failed me. It gives a a good prediction of the rendering of a lens. Now, as an example, let's look at the lens filming me now, which is the Viltrox 35mm f1.8. It has two extra low dispersion elements, which make about 15% of the glass used. So that will put it in the mostly flat category. Now I will change the lens. Now the lens filming me is the Falkland 35mm f1.5. This lens has no extra low dispersion elements, and its group complexity is 1.5. So it should put it in the highly poppy category. It would be interesting to compare the rendering later. The lens filming me now is the Tamron 35mm f1.4. It has 4 extra low dispersion elements, which puts it squarely in the flat category. So, what do you think? Does this model work? I hope so. One more rule of thumb, actually two. The first is avoid lenses that have APO, the letters APO in their name or description. Those lenses are putting emphasis on reducing chromatic aberration, and they probably contain more than enough extra low dispersion glass. That excludes Leica lenses. I'm not saying that they are any better, but I would never know. I'm trying to restrict myself to items that are remotely affordable. Next, if you look for a poppy lens and you have a choice between two lenses with similar specifications, you are probably doing the right thing if you pick the smaller one, because it will have a simpler design that uses more high refractive index glass. Next we will discuss past and contemporary trends in lens design, and try to see where the near future is leading us. Thank you for watching.